Hello, my name is Sina Ghanaat, and this is the final course project for my Mechatronics 1 course at the Toosi University of Technology. In this project, I will design and simulate a wind turbine from scratch, but at the meantime, I will explain how to use Simscape Simulink to do so. Now, with no hesitation, let's look at the project outline. First, I will design the wind turbine structure with Simscape for simulation. Then, I will add aerodynamic effects to the model. And ultimately, I will design and implement the control schemes for pitch and yaw angles. Okay, let's start with the structural design. Here, you can see a simple sketch of a wind turbine. A wind turbine has four major structural components. Rotor blades are most important parts in a wind turbine. The majority of the horizontal axis wind turbine have three blades. Having fewer blades reduce drag, but two-bladed turbines wobble when they face the wind. So, due to some stability challenges, three-bladed turbines are more desirable. A blade is simply an airfoil mounted on the hub, which the hub rotates the low-speed shaft in nacelle. There is a lot going on in the nacelle, but for the sake of the time I will mention the most important components. As I said before, the blade mounted on the hub rotates the low-speed shaft. This shaft then connects to a gearbox, which rotates a high-speed shaft connected to the generator. There is a brake system in the nacelle to stop or hold the rotor. The pitch angle control system is in the nacelle as well, but the yaw angle controller is inside the tower. However, in the Simscape, I will consider the yaw angle controller inside the nacelle too. The whole design procedure of this is pretty time-consuming and is not a difficult task to do. However, for the educational purposes, I intend to design three major parts: the tower, the nacelle, and an individual blade. Then, for the next task, I will use a pre-designed model. So stay with me. Alright, let's continue. Now, in order to design a wind turbine, you might need some specification about that wind turbine. For example, the blade model or the dimensional values or mechanical properties. But this information may not be available very easily or at least in one piece. But I found a very useful website called nrel.gov, which has a brilliant material related to renewable energy, specifically about wind and the wind turbines. I myself at least found one related paper about wind turbine specifications, which helped me a lot alongside the project. Okay, let's get back to the Simulink. Now, in order to design the wind turbine, we're going to start from the tower, then up to the nacelle, and just a blade that we're going to design. So let's go to the library. Then in the Simscape section, we're going to use the multi-body section. So first of all, for every Simscape simulation and modeling, we need a solver configuration. So I'm going to put that in here. Now we're going to define a mechanism configuration alongside with an inertial frame, a motionless frame, that other frames are actually determined by this. Then I'm going to attach that here. Now we're going to design our tower. So I'm going to use the revolved solid because our tower, if you look at it at the front, it's a half cone. So if you if I design the section of that half cone, then revolve it around its vertical axis, then I will get the tower itself. So if you see here, it's a cross, it says the cross section. I'm going to define it. So for the dimensions of the tower, we have base radius of 2 meters and top radius of 1.15 meters, and the tower height, it's actually 100 meters. So what I'm actually going to do is define it like this. So these two digits, these two numbers are actually the X and Z values for the cross section. So if I'm going to start from the base radius, I'm actually using 0, minus 50, 2 meters, minus 50, 1.50 minus, not minus, actually 50 this time, and 0 and 50. And if we do this, brilliant. Now we have our tower. We click apply OK, brilliant. Now this is, as you see, I do the minus 50 thing in the revolved solid. This is because the section that I have done in this way, if I wanted to actually define a mass in the middle of the tower, it will be much more easier for me. But in order to do that, I should actually, and then I must transform the inertial frame to the middle of the tower. So I'm going to use the rigid transform block. I'm not going to use the rotation. I'm going to just do the translation, standard axis Z, and I'm going to move it 15 meters above. Now I'm going to use the same to get to the top of the tower in order to design the nacelle. Okay, brilliant. Now we have the tower. So let's go for the nacelle. Now, in order to go to the nacelle and the tower actually divided by some kind of gear section, which the yaw actuator actually move or rotate the nacelle about the tower. So I'm going to define that as well. So I'm going to go to the body elements, slanted or solid, because I just want to everything be very simple. Okay, now that gear actually you can define a pretty much similar to any gear, any huge gear actually configuration. Well, let's go with diameter of 2.3 meters and thickness of 0.1. Okay, let's see what we've got. Brilliant, this is great. Now we're actually using this. Now similar to the tower, we're going to use some rigid transform frames. Oops. Okay, now just put that here, rotating this, and this. Now this is again the same stuff that we dealt with before. I'm going to just go and half height or half thickness of the gear thickness, so this will do the job. Again here to get to the top of the gear. Now brilliant. So this gear here actually is connected to the nacelle, not with a solid joint. It actually rotates about it. So we are going to use the joints section here. Now using the revolute joint. Brilliant. And since the tower is the base, I'm going to use the base here because the joint actually the follower actually revolute or rotate around the base. Now we're going to define our nacelle. So we're going to the body elements, brick solid. Simply and similarly, I want to just make everything as simple as possible. Now just going to define the dimensions. 6, 6, and 13 will do the job. Okay, now see, let's go. Oh, brilliant. Now that's great. Okay, now we're going to need to define this solid and transform it with respect to the joint. You can do it if you have the sketch in front of you, or or other resources that you have. I have luckily the numbers that I want to, so I'm going to use this and define the position of the center of the nacelle. I'm going to use Cartesian translation method. Now this will be, minus 3.5. This will be 0, and this will be 3. And after the simulation, I will show you a very interesting stuff. Then I'm going to actually do this. This is brilliant. Now then I've done this. Let's Control D it and see what is actually happening. Looking, it's brilliant. That's the tower. Just make it much more bigger now and pan it. That's the tower we have declared. And that's the gear that we actually done. And you can see that the nacelle is here, but in a very odd position. This is because all the extrudes and all the 3D tools that Simscape use is always alongside the Z axis. So I have to rotate this solid here. So I'm going to use rigid transform, again base. So here, good. Now 19 degrees. Orbit, standard axis plus Y, because I just want to point the Z axis to the other direction. Now, okay, this will do the job. Let's see. All right, brilliant. Now you can see the tower. Actually, very uncomfortable with this mouse that I'm having right now. You can see the tower, the nacelle, and finally all the other stuff. The designing procedure for the other components of the wind turbine is actually similar to what we have already done here. So, except for the blade, because the blades are actually airfoils. So the airfoils have a very particular and specific cross-section and design. So we have two options in order to design airfoils. First, we can actually design them and directly in the Simscape, which is pretty much time consuming and very hard to do. Or we can use some other CAD softwares and import the resultant step file from them into the Simscape and use it there. So I've actually done that. I've actually downloaded a very beautiful airfoil from GrabCAD and as a step file, and I used it in this project. You can do as same as what I've done, or just design it by yourself. If you intend to design it by yourself, there's a pretty good website called Airfoil Tools, which you can actually have the airfoil cross-section specification or other aerodynamic properties like drag or lift coefficients, other stuff like that, or polar graphs. And it's a very good website, and I've used it in this project, and I will discuss that later, for the aerodynamic effects that I'm going to exert on the blades. But rather from that, let's get back to the Simulink. Actually, in order to import the step file, you can use this block here, file solid here. And now I actually bring it down here. Then you will going to choose your step file. My step file is actually here. Now let's see. Brilliant. This is my step file. This is a pretty much a very beautiful airfoil. And just bear that in mind that actually I'm actually going to use this as a visualization file only. So what you see in the simulation finally, eventually, is a very beautiful wind turbine rotating and generating power, but the properties of the blades which are going to generate power is or maybe not as same as this airfoil, but because it's pretty much more easier for me to download a prepared model of an airfoil. I've actually downloaded an airfoil, but I'm going to minimize the effect of its inertia and the mass, and I'm going to define my own desired mass and inertia later on. So this is I just wanted to show you how you can import step file, and then we can discuss this later. So if you just wait a little bit, I'm going to complete all the designs and then come to you some moment later. So stay with me. I'm going to be with you pretty much soon. Thank you.
2,000 years later.
Okay guys, welcome back to a pretty challenging wind turbine project in the Simulink Simscape library. Now, in the meantime, I've actually completed the structural design of the wind turbine, but as you can see here, I've added a couple more blocks to the project. Now, there is a control unit block, there is an aerodynamic effect block, there is a supervisory control block, and there is a blades block. So, let's start with the aerodynamic effect block. As you can see here at the left side of the block, there is a wind input. So I've actually used the signal generator block in the Simulink to generate a wind speed and wind direction to out to my simulation. So the aerodynamic block actually imports the wind speed and wind direction. But let's see what we are looking for. Now, the forces acting on the blades are lift and drag forces. There are other forces too, but these two are pretty much important. It's the most important forces actually there. Now, the lift and drag forces are a function of lift and drag coefficient, where the lift and drag coefficients are a function of angle of attack. Now, due to our understanding of the blade, the wind, and the wind, we know the angle of attack of our blade. So if we know the angle of attack and the function, we can find the drag and lift coefficients, and ultimately we can find the lift and drag forces. So how we can find these function? So there is a way. If you actually look at the beloved website of airfoiltools.com, you can see for a specific airfoil, for example NACA 2015, you can find a couple of useful information here. For example, the cross-section of the airfoil, some kind of graphs, which two of them are very useful for us. One is the lift coefficient versus alpha, which alpha is the angle of attack, and the drag coefficient versus alpha, which you can see here. Now, if we use these graphs and use these graphs as a lookup table in the Simulink, then for each alpha we can have a specific CL or CD. This is what we actually do for our airfoil. Let's get back to the Simulink. Now, opening the aerodynamic effect block, you can see here that we calculate the angle of attack. This is pretty much straightforward. Now we are going to obtain the lift and drag coefficients. So when we have the angle of attack here, we are going to feed it to a lookup table block block in the Simulink. Now the input is the angle of attack, and the output is the resultant graph, which we can have for each airfoil at the website. Now this is the same for drag coefficient. Then the CL and CD will be fed to the force calculator, and ultimately we can find the resolved moments. Now, then we exert these torques on the blade by using the external force and torque block. Now, these blocks actually prepare the force to be exerted on the blade itself. So let's go to the blade. This is the blade block. In the previous section, I've actually designed a blade by importing the step file. Now here, I'm actually going to show you the much more complex side of the story. Now, if you can see here, this geometry block here is actually the blade itself. This pin is a intersection between the blade and the hub. It's actually kind of a welding joint. Now there is a inertia block here, which is very interesting here. If we can open it, there is a 0.01 radius inertia and a very high mass and moment of inertia. This is because of when I'm going to design my airfoil, I'm going to put the center of gravity of the airfoil and other mechanical properties at which which pleases me, which I desired it. Now, when we go to geometry and look at the, for example, base cycle, if you look at the inertia, you can see it has a very low mass. So that means that all of the forces which effect on this blade will actually affect on this inertia. So this a segue kind of method to simplify the designing procedure. Now, the resultant of these forces will be two moments, a bending moments, and resulting two moments, a bending moment and a lift moment. So when we go to nacelle to see what's happened when these forces exerted on the blades, we first of all go to the hub. Now, in the hub, or actually let's start with the pitch system. Now, in the pitch system, the forces of the B1, BPA1, and all the forces acting on the blades, well, we can see them here. Now, the lift moment, the lift torque, actually try to rotate the rotor, and the bend moment actually repel the changes in the pitch angle, while the actuator try to reach a suitable pitch angle. So these linkages are for the pitch angle actuator, and this part here are just for defining the revolution of the blade with respect to the hub and rotor. So there is a rotor subsystem here which transform the hub frame to 6 frame, blade 1, 2, 3 and actuator 1, 2, 3 frames. Then these frames will be used in order to determine the linkage and finally the simulation. So let's see what linkage look like. So a linkage actually accept the pitch control command, and this is a two-way connection block. It's a very useful block in the Simulink and Simscape. It's reduce the need for signaling and wiring in the Simulink pretty high. It reduces a lot, and while the Simulink doesn't actually provide us with any of this, but it's actually supported it. So you can find this block in other libraries. I don't know which ones, but in this newer version of the MATLAB, you cannot find the two-way connection block in the Simulink library itself. So there is a pitch control signal here. Then we convert it to a physical signal. Then this is actually the force acting on the cylinder. Okay, now this is actually going to the force. The resultant is a position and a velocity. This position and velocity will be taken back to the pitch control structure we'll be talking about at the moment. Then there is a rod and cylinder here. The rod actually connected to a small pin with a universal joint, and the cylinder is connected to the hub with a spherical joint. This is actually a wrap up of what a hydraulic linkage might be, but it's much more complex, but this is a simplified version of it. Then this block is actually a interface between the linkage and the pitch command. It's nothing very seriously. You just some kind of structural signals. We take all these positions and velocity couple values and put the velocity with each other and put the positions with each other, then use it as a signal. Now, so this is the pitch controller, but look at this joint. This joint actually play a very significant role in the behavior of the wind turbine. Just look at the spring stiffness and damping coefficients, which are both 0. Okay, enough with the pitch system. Now let's go for the next step. So the next step is the hub. So if you actually look at the hub, the hub has a revolute joint with respect to the nacelle. So this revolute joint is actually a active joint, but the driver that actually makes this joint active is the hub itself. So it's the blades. So the blades, which are here called the rotor is a follower and the nacelle is the base. But the velocity, the angular velocity of the rotor actually comes into this block, which produce a torque, and then this torque will actually feed into the joint and became the motion of the hub, which fundamentally rotate the blades. So this is actually an inverse dynamic kind of loop, which we can see here. We actually get the velocity, the angular velocity, so the kinematics, and then we find the joint torques of the revolute joint. Now, after the hub, this low speed shaft will go into a gearbox and brake system. This is an overview of it. It's a brake system on a lower speed shaft, so it must be a very powerful brake. Then we have some some levels of sets of gear, and finally the output of the last step will be fed into the generator here at the last part. Now, the whole structure of the nacelle has been explained in precise detail as much as possible. Now, what is the control unit? So, in order to simplify the control unit for this project, we have two control structures for yaw control and pitch control. So look at this. We can have a desired rotor speed, which ultimately give us the efficient power generated from the turbine. Then we have the actual speed. This will result in a desired angle of attack. So we have an angle of attack which is a desirable. Then the inflow angle, which is what the angle of the wind is coming to. Then the angle of attack will be compared with each other. Then a pitch angle command will be generated. Then these pitch angle will be fed to a control structure with suitable gains, which can command the valve position for the pitch actuators. But for the control structure, for the yaw control, we have a yaw command. So we actually have a position. Then we have the nacelle yaw angle, which then resulted in a yaw rate command for the motor to control it. So the speed of the rate of the yaw command then will be fed into a controller to produce or generate the torque command for the motors. These two structure actually very easy ones, but very tricky at the same time, have been implemented in this actually block here. Now the final block here that I'm going to talk about before the simulation is a supervisory control block. This supervisory control blocks has actually been imported directly from a similar example by MATLAB itself. This is a state flow block here, which determine which state the turbine is in. So it produce, if it's for example, if the wind acting on the blades touch an upper limit value, then a pitch brake command will be generated, causing the blades to position themselves in a way that the most drag and less lift generated on them. So then after that the brake system will be engaged and stopping the turbine at once. So this is it's a very interesting part. If you can see in it, there is some 4 state of the turbine parked, which actually is completely vividly obvious what it means. The startup, which is the start of the turbine but not generating power. So there is a generator trip, which is 1 here. That means no power is generated. Then it's at a sufficient speed, the generators start to engage, and finally if these conditions or this conditions starting to occur, then a brake state will be engaged. But another interesting thing about this turbine, this actually project, is the pitch control command. Let's see it here. The pitch control command actually is a valve command. So how we are able to determine the valve command, so ultimately the valve position and the angle of the pitch. It's a very interesting part here, because as you can see, a valve, a cylinder piston actuator, prismatic actuator, is actually a 4-bar linkage mechanism. So since it has a 1 degree of freedom, we can precisely find at what angle what distance does the cylinder has from the base or from any other optimal or desirable surface that you want. So, and vice versa. So actually you can have the angle to extension mapping and extension to angle mapping. So when the pitch command's generated, it will be fed into this lookup table to then map into a extension value. Then this extension value will be the valve command ultimately. In other hand, at the supervisory control block, the pitch control will be fed into the extension, the pitch command actually would be fed into the extension to angle. So it's actually the vice versa of the aforementioned lookup table to get the pitch angle. Now, after that, all these stuff has been explained to you in a precise way. I hope you understand it well. So let's start the simulation and just see a very beautiful part of this project. Now we click on the run, okay, to see what's actually happened in the simulation. Now, since my laptop doesn't feel powerful enough today, I have the simulation as a clip in my desktop right here. So let's see what happened to the wind turbine. So bear in mind that around 50 seconds, the wind speed will touch the upper limit of the turbine resistance. So now the turbine slowly start to gain speed. The pitch angle is starting to adjust itself. Brilliant, very good. If you just look carefully enough, you can see a little bit of yaw angle changing in the